So the final talk of the session is Elias, who's going to talk about secure calling conventions.
Great, thank you. My name is Elias Storme. I'm a PhD student at KU Leuven, supervised by Dominique Devriese. And I'm going to talk about my work putting secure calling conventions for CHERI in practice. So first of all, I'm working in CHERI Risk 5. Most of you are familiar, I assume. And with capabilities even more, so this is just a schematic representation that I'm going to be using. Our memory is always up, and the stack grows always down, like in Risk 5. So benefits of capability machines you've also already heard, and we're going to zoom in on the compartmentalization. Because compartmentalization models very often have separate stacks for each compartment, which is secure and everything. But what would be nice is to be able to securely share a stack between adversaries. Because not only would that save memory, it would also save instructions switching between the stacks in theory. And in order to allow that, there's two crucial components which must be gotten right. The first is return encapsulation, and the second is stack revocation. And for both these components, there's no real obvious answer. But there's been proposals in literature on how to address these. So the first, return encapsulation, just handles so when a caller calls another function, the callee, they don't want the callee to have access to their own stack frame. So what they do is they release authority, so that in the end the stack capability looks like this. And the question is, how do we get back to this situation? So obviously the authority should be saved and encapsulated in some way, but the question is how can we achieve this? And the second deals with kind of a semantic issue with C-like languages, which is that the unused part of the stack is assumed to be empty, but in practice this will not be the case. And the problem with that is not so much the data, it's the capabilities that can be left there. Because if some rogue capability is left lying around in the stack and it has authority over something that the currently executing program should not have access to, this can lead to privilege escalation. So there's been many proposals in literature about how to address these two crucial components and build a complete calling convention out of them. Most of these have formal verification, but they obviously make some assumptions about practical details, which must be addressed if we want to put them into practice. And so towards that goal, we're contributing in three ways. The first is addressing a practical issue with capability compression. Second, we contribute implementations of the calling conventions and variants into LVM. And thirdly, we're looking into benchmarking to determine which of the mechanisms perform best in different ways. This is still a work in progress. We're still working on it, and so some contributions will be farther along than others. So to elaborate about this capability compression, as has been said before, the CHERI uses a kind of lossy compression for capabilities in order to save memory. It cuts the size of the capability in memory in half. But theoretical calling conventions ignore this compression. I'm sorry. Skip. Yeah. And so this compression is a floating point ASCII encoding. I'm glossing over a lot of details here to get the message across, which is that the top and so the bounds are encoded with a mantissa, which is then and a common exponent. And the takeaway from this is that the bigger the capability gets, the coarser you have to align your bounds. So why is this an issue? Well, as I've said, the theoretical calling conventions ignore this compression because it's hard to reason about, obviously. But they also do an operation which we call stack splitting, which does not play well with this capability compression, and I'll show you why. As mentioned in the return encapsulation, what happens often is that we do this, and so we restrict the authority of the stack capability to the boundary between, well, I should point here, to the boundary between the caller and the callee stack frame. Issue is that with how C and C++ is compiled right now in LVM, this boundary is only guaranteed to be aligned to 16 bytes, which is quite fine talking about alignment in this way, because the implication of that is that the maximum stack size, which is imposed on us because we want to align to these 16 bytes, is 16 kibibytes, which is orders of magnitude smaller than the default stack size on Linux, which is 10 megabytes. So we've come up with a solution to this problem, which is to split the authority of the stack capability into two parts. The first is the active stack, which will behave like the normal stack capability, and will be below this maximum size of 16 kibibytes. And the second is a reserve stack, which will act as a kind of authority reservoir, from which we can get authority to add to the active stack capability. And adding this authority to the active stack capability is, we call this replenishing. So this is a kind of more practical example with, with some numbers you can get an idea. We're executing. The active stack has dropped below 18 kibibytes, which is our chosen limit below which we will do the replenishment operation. And when we replenish, we take authority from the reserve stack, we add it to the active stack, and things should look like this. The active stack is now extended by 8 kibibytes, but is still smaller than the 16 kibibyte limit. Some questions remain, which we want to address by doing a prototype implementation. The first is, where should this reserve stack capability be stored? Current answer we have is the bottom of the active stack, because that's a nice predictable place to store it. The next, can components share this replenishment algorithm? Yeah, they should be, as long as we don't store any capabilities in along with this replenishment algorithm. Third, compatibility with stack objects. This is an issue because if you were to pass a capability for a stack object to the replenishment algorithm, it should be able to tell that it is not the stack capability, but instead something different. Because otherwise you may get into a situation where the capability of that object is extended and some kind of more privilege is gained. And finally, where do we want to check for replenishment? This will depend on some performance characteristics and how small we are able to get the check for if we want to replenish. But for now, we're assuming that we do it every call. Next, we've implemented some calling conventions in LVM, and we've done it in such a way that we can create variants of the calling conventions as well. And the motivation for doing this implementation is to discover practical questions and trade-offs. So we believe that the best way to discover practical difficulties is just to do the implementation and see what comes up. And the second thing is that this enables benchmarking through also the use of these variants to mix and match between different mechanisms to evaluate their performance. Why do it in LVM? Because it's obviously a big project with a lot of code to familiarize yourself with. The benefit of doing it is, of course, the support for CHERI that LVM has. There's no other compiler of the size that has the support. And with the maturity of the LLVM compiler, we also get access to a large corpus of C and C++ code from which we can get code to benchmark. Now we return to these components which I introduced before, which have to be gotten right to get a secure calling convention. And we've treated these as being orthogonal in the sense that we can choose one and choose another and combine them and create a calling convention in that way. So to remind you, the return encapsulation is regaining the authority that was lost upon a call. For this, we are considering actually 3 options, but the third option is doing nothing, which is not interesting. But the 2 options we're considering, we're implementing our sealed entry capabilities, the classic sentry, which are supported by the stock CHERI architecture. And then indirect sentry capabilities, which were introduced by Bastien in the talk before. So instead of doing this, which you have to do with sentry capabilities, using a trampoline to do the return, you hardware accelerates part of that, and we include these indirect sentries to evaluate what kind of performance is to be gained there. The next stack revocation, so clearing the presumed to be empty space. Again, 3 options, but one of them is none, so I've only listed 2. You can clear everything, as is the case in the local capabilities calling convention. While this may be inefficient in some cases, it is very much effective. And as the chariot work apparently demonstrated, it may also be not that inefficient. But then secondly, there's also a new mechanism called uninitialized capabilities, which are kind of clear by need. And with clear by need, I mean, well, I'll explain the mechanism. The capability is divided into 2 permission regions. So the upper region has the normal permissions, in this case read-write. And then below the cursor, you only have write permission, which forces you to override any part of this, in this case, stack, which you want to use. So in practice, passing the stack capability to the callee will look a bit like this. You have the caller stack frame, the authority is restricted, and so the callee only gets capability, gets a capability which is fully write only, and every part they overwrite becomes readable to them. So these orthogonal components summarized into a table look like this, and this is to show our implementation status. Filled in dot is fully implemented, and the other part we're still working on. Then onto benchmarking. So this is mostly still an exploratory stage, but we have an idea of the metrics that we want to measure. So execution speed is an obvious first. That's people are always interested in that, and yeah, because the calling conventions obviously add some instructions. It's good to measure the overhead there. Second is stack usage with the use of, for example, the trampoline. Some additional stuff is put on the stack, and it's important to measure that as well. Binary size is interesting for a similar reason, so extra instructions and extra instructions for putting the trampoline onto the stack. And finally, compatibility is more of a qualitative measure because it's, well, I guess you could measure it in some way, but then the question of how becomes difficult. So the question of measuring compatibility is which C patterns are supported and which patterns break when using this new calling convention. And to automate this, we propose using this random testing framework proposed by Christian Lindick, which includes random generation of a lot of common C patterns. And by using this, we aren't sure that the most common C patterns are supported, but the patterns that are included in this framework, we will be more confident that there's no weird edge cases because we've run a lot of random test cases. Now, the calling conventions that we've looked at are all using experimental extensions to the CHERI architecture, so there's no hardware available, but of course there's SAIL, as many of you are familiar with. This is, however, not cycle accurate, so not ideal to benchmark with. So to address that issue, we're still we still need to decide if we're going to modify an RTL implementation, like some of the available RISC-V cores, or if we are going to use GEM5 to only simulate the memory subsystem, since we hypothesize that the main bottleneck will be in that place. And then finally, as to benchmarking software, we want to do micro benchmarks as a first step. These micro benchmarks will be the code generated by the random testing framework. But after that, macro benchmarks would require a little more effort because we have to recompile a lot of code. But beyond that, it should be possible to take some software adapted for CHERI and do benchmarks with it. So to conclude, with these secure calling conventions, we want to increase the granularity of the compartmentalization by allowing a shared stack. And we contribute towards that goal in 3 ways: by addressing practical issues, by contributing an implementation, and by doing benchmarking. Thank you.
Thanks very much. There's a couple of minutes for questions. Yes?
For the stack revocation bit, and I might be misunderstanding something, but naively I would think you could just do that by having each function as it adds to stack pointer, pops at stack frame, just also call clear capability tags on that region. Is there a problem with just doing that? What's the complexity there?
So the main issue that we're considering there is that you might be some levels of adversary deep. So the function that you want to protect might itself be called by some malicious function, and when that your trusted function then calls the adversary again, there might be something on the stack which was put there by the previous adversary, which Yeah. Shouldn't be there.
Simon, you had a question.
More of a comment, actually. If you want to change the RTL, by all means reach out to people in Cambridge and ask, because we may be able to help, because we've got quite a lot of infrastructure and a big farm of FPGAs, so you might be able to then get access to...
Very nice, yes.
Question number?
So yeah, this is very nice work. One question is if you also want to benchmark against CHERI BSD kind of approach and see not just, I mean, whether it's worth having a share stack at all.
Well, yes, that would obviously be interesting. I'm having to think quickly. The issue with that is that there may be a lot of things that need to be adapted to allow using these new calling conventions in environments of CHERI BSD, because CHERI BSD obviously will not expect, for example, initialized capabilities to an uninitialized capability to be the stack capability. So, like system calls may not work, things like that, because you're passing a strange kind of capability back to the system.
Do you want? Yeah, I mean, I guess I didn't mean to implement your stuff in CHERI BSD, but would you be able to model calling conventions that's more like theirs in your framework, and simply test against it the kind of simple random things, random program like this?
I like that. Oh, sorry for the misunderstanding. So every time I said doing nothing, I meant using the calling convention that's CHERI LLVM by default emits, which should be just compatible with CHERI BSD. So the baseline we're measuring against is the calling convention used on the CHERI system.
Okay, comment from Robert?
Yeah. So obviously we should very happy to chat over lunch especially, but I noticed that in your evaluation criteria you weren't considering kind of like architectural, micro-architectural viability for the changes, and a big part of the co-design cycle has been saying, well, sorry, you can't write to the register file twice in one cycle or one instruction, or yes, but this funny thing will happen with pipeline forwarding or exception delivery and that kind of thing, and it would be worth maybe spending a bit of time thinking about that. You can answer some of those questions without necessarily doing a full RTL implementation. The other thing I was going to comment on was, I think this blend of potential blend of taking together trace data and simulation, whether using Gen 5's cache models, whatever, it goes a long way. We use that for some of our own work, rather than saying, let's go implement everything. We say, let's take a memory trace, play it against a cache model, and then see what the behavior is, or look at the instruction density as a result of that. It's like quite a good methodology to use, especially when you don't yet want to commit to specific RTL implementation, because to do so would be very time consuming, for example. So, but it would be great to chat over lunch more about evaluation and approaches.
Right. Thanks very much, Elias.